Welcome to another special edition of Daily Airline News focusing on the loss of Air India Flight 171. I'm Geoffrey Thomas and I'm delighted to say joined by my co-host Richard Godfrey in Frankfurt. Good morning, Richard.
And good afternoon, Geoffrey.
As previously announced, today we're going to discuss the fuel system and electrical systems of the Boeing 787-8 aircraft. In particular, what can cause sufficient thrust to be able to take off, but insufficient thrust to maintain altitude? What can cause a catastrophic electrical failure? What can cause a catastrophic electrical failure at the same time as lack of thrust? What is the connection between the fuel system and the electrical system? In this episode, we'll go through these points one by one. So let's start with a fuel system overview. Richard, can you give us that overview, please?
Sure. So the fuel tanks, there's a left wing tank, a center tank, and a right wing tank, and surge tanks in the outboard wings. The total capacity is 126,917 kilos. That's around 279,000 pounds. The wing tanks are around 42,000 kilos each, and the center tank is just a little bit bigger, 42,900 kilos. The center tank feeds the engines first, as long as it's been filled with fuel, and then the wing tanks. And there is an automatic fuel balancing between the tanks. There are scavenge ejectors which pull remaining fuel from the outboard parts of the wing tank, and the fuel jet creates a kind of low pressure zone, a Venturi effect, that sucks in residual fuel from the outboard parts of the wing tanks, so every bit of fuel can be useful. The main fuel pumps are AC electrically driven, and they are booster pumps. The Boeing 787 system is much more electrically driven overall, but it is not fully independent of mechanical engine-driven components. There are no cross-feed valves in the traditional sense. The 787 has an engine and APU fuel feed manifold logic, and there isn't a single pilot command controlled cross-feed valve like older jets have. So the fuel system is highly automated, and it reconfigures itself using multiple valves which act in effect like a cross-feed, but it isn't a single dedicated cross-feed line.
So, in that case, how does the fuel get from the fuel tanks to the engines?
Well, we're showing a schematic of the Boeing 787 fuel system. There are valves, pumps, heat exchangers, filters, meters, splitters. It's quite a complicated system. The valves and pumps and meters of the fuel quantity and fuel flow are electrical, and the fuel filters and the fuel heat exchanger are mechanical. So the system includes the left and right AC-driven boost pumps, isolation valves, fuel feed manifold logic, can hardly say it, fuel line pressure monitoring. So, for example, if there's a blockage in the fuel supply, the delta pressure sensors will detect it. And if you get a ICAS message saying engine fuel filter clog, the system will automatically bypass the fuel filter and send a fuel filter bypass ICAS message. So you know exactly what's going on if that happens. And if all the AC power and DC power fails, in other words, a total electrical failure beyond the capabilities of the RAT or backup power, then there will be no delta pressure readings available, no automatic detection of filter clogging, and no ICAS messages will be generated.
So what happens to the fuel system if the electrics fail, Richard?
Yeah, well, this is what we previewed in the episode yesterday. In a severe electrical loss, so I mean essential engine feed pumps remain powered, but not by the AC, as we said to start with, but a backup DC essential bus or RAT supplied bus, things will still carry on electrically. With a catastrophic electrical failure, by that I mean no AC, no DC, and beyond the RAT capability, then there is still a manual backup, a mechanical backup. Suction feed is controlled by the engine driven fuel pump, EDFP. If the fuel booster pump fails, and suction feed from the main tanks via this EDFP will function even if both fuel booster pumps fail. Though there are some limitations. The EDFP provides mechanical suction to pull fuel from the tanks to the engine, but can sustain the fuel delivery without the boost pump pressure as long as there is no vapor lock or blockage.
That begs the question, what can cause a vapor lock?
Well, vapor lock occurs when fuel vaporizes prematurely in the fuel lines or pumps and interrupts the normal fuel flow to the engine. It's especially dangerous when you get to the suction-fed mechanical backup system. And that can lead to an engine flameout. And there are 5 possible issues: a low ambient pressure, a high fuel temperature, a low fuel pressure in the suction feed mode, a low fuel quantity, and the fuel composition.
What can cause a fuel blockage, Richard?
Well, there are even more possibilities. And if you get a ICAS message, a fuel filter clog, then you need to take it seriously. The 7 possibilities are contaminants in the fuel, that the fuel filter itself is blocked. There was icing in a previous flight at high altitude, and water particles then, when the fuel temperature increased, you have to bear in mind at altitude, you can go down to temperatures like minus 50 degrees centigrade or even colder. So when the fuel warms back up, then you will have water particles in the fuel. And that's bad news. Another possibility, a valve failure, it closes or it jams. Another is a pump failure. And another issue is collapsed or damaged fuel lines. And finally, a tank vent gets blocked. So when you try to take fuel out of the tank, the pressure in the tank, air pressure, will be automatically adjusted via a vent. But if the vent is blocked, then that can't happen. And the Boeing 787 has a fuel oil heat exchanger in both sides, both engines, and fuel temperature sensors and fuel circulation to avoid cold soak. And it even has water scavenge ejectors to mitigate any water contamination in the fuel. So it's a horrendously complex system, and there are a large number of possible causes of problems.
Yeah, indeed there are. What about an electrical problem?
Yeah, well, there's another long list. We're showing a schematic of the Boeing 787 electrical system. So each engine has two generators, a main and a backup. There's also a permanent magnetic generator, or more precisely, a permanent magnetic alternator. And if one or more of the IDGs, the direct drive generators, fail, the aircraft automatically shifts loads, electrical loads, to other sources. So if both IDGs go and their backup goes, then the APU is a source, or the RAT is a source. There's battery backup as a source. And this will lead to load shedding, and that will lead to partial system loss. Now, we've mentioned before the APU takes at least 60 seconds to come online. So it's normal operating procedure to switch the APU to off once engine start sequence is successful. And so when you take off, you've got both engines running, and you're running the electrics from the integrated drive generators, the IDGs, in both engines. If that all fails, then, as we also have seen, the RAT will relatively instantaneously deploy and will then supply essential electrical equipment. So emergency cabin lighting, for example, and not the normal cabin lighting, but also the key cockpit displays and communication systems for the and navigation systems for the pilots.
Mm. So what systems on a 7878 are powered when both engines, the APU and the RAT, provide no power?
There's still battery backing systems on the 787-8 when you've got no generators, APU or RAT, and those battery backup systems will keep the flight instruments, a minimal selection going, the flight control systems, again a minimum backup level. It will maintain the APU start logic. It will maintain one radio for communication, the emergency cabin lighting and lighting in the cockpit. It maintains the fire protection, the braking system, and the oxygen activation system. But battery power is time limited, usually 10 to 20 minutes. And the goal is to allow the APU to restart and then to enable an emergency descent.
Yeah, it's pretty impressive though, isn't it?
Yeah,
So,
back up to the backup to the backup.
yeah. So what gets checked on the fuel system and the electrical system before a 787 takes off?
Well, there's a whole set of procedures that they go through. The first one is when a flight crew uh, receive an aircraft. So there's a handover of the aircraft to the new flight crew, and they go through the receiving aircraft procedure. So you go through the technical log, the maintenance log, you walk around and do an external inspection. You prepare the cockpit and you check the safety systems and in the cabin and the cockpit. You do a system initialization. You'll check the fuel quantity and the distribution. You will do configuration cross checks. You will go through the review any deferred items on the minimum equipment list or the configuration deviation list. This includes then discussions with ground crew, engineering, cabin crew, and the dispatcher. The fuel quantity will get checked. The fuel quality, however, will only get checked if required. And the flight crew assumes that the fuel quality is correctly checked by the ground handling staff. The electrical system gets checked after engine start. And when you transfer from ground power unit or from the APU, you make sure there are no ICAS alerts. You check the voltage and frequency is within limits, and the load levels on the generators are not abnormally high. Galley ovens, for example, may well be operating during taxi, but they are deliberately switched off during takeoff. And there's quite often an APU report just prior to gate departure, which comes through on the ACARS system. So there's lots of information, lots of checking going on.
So when the aircraft goes through the engine start and the taxi, what is checked before takeoff on the fuel and the electrical system?
So the fuel quantity will be checked against the load sheet, and the electrical system synoptic page in the cockpit will be displayed, and the generator loads will be checked, and they'll check obviously for no faults or caution messages on the ICAS system. And there are several checklists they go through. So prior to engine start, another one after engine start, another one prior to taxi, and another one just prior to takeoff. So they're continually checking that everything's okay.
Now, Richard, are there any noise abatement procedures for Ahmedabad Airport that require reduced thrust?
Nope, there are no specific noise abatement procedures. There is a global best practice scheme which foresees a climb at full takeoff thrust to, say, 800 feet or 1,000 feet above the aerodrome elevation. And then you will reduce thrust to a so-called quiet climb. So I assume that general best practice is followed. But in this case, with the Air India flight 171, we didn't even get to 800 or 1,000 feet. So I don't think there would have been any thrust reduction, which is due to noise abatement.
Yeah. So, what can cause a catastrophic electrical failure?
That's a key question. And, to get a dual engine failure and the APU not online, that will cut off the main AC power completely. And the Boeing 787 has lithium ion batteries, which have a known risk of thermal runaway and fire and explosion. In 2013, there were incidents with Anna and with JAL due to battery thermal runaway, and that actually grounded the entire 787 fleet globally while that issue got resolved. And a failure or isolation fault, for example, arcing or a short circuit, can cascade and result in a system-wide power loss.
But we must also point out that since that lithium-ion battery issue was fixed, there hasn't been any incidents since then, have there?
No. So 2013 is 12 years back.
Hmm.
And since then, no battery incidents.
Hmm. Can a leaky toilet waste water seeping into the electronic equipment bay cause a catastrophic electrical failure?
Well, missing or damaged or deteriorated sealant and moisture barrier tape or tape dams can allow a water leakage from the potable water system due to improperly installed waterline couplings and water leaking then into the electronic equipment bays from the floor above in the main cabin. And as you pointed out in a previous episode, the equipment bay is right underneath when you stepped out of the forward toilet in the 787, you can see the hatch to the equipment bay right
Mm.
there. And during rotation, any accumulated water will flow aft and down due to gravity. If there's a path for the water through the sealants and the water barriers to the electronic bay, then water will find that path, and water ingress will be catastrophic. Now, Boeing issued an alert on the 6th of March 2024 requiring a number of checks before the next flight of each 787. And the FAA introduced an airworthiness directive and made a notice of a proposed rulemaking in their register on the 26th of December 2024. And the FAA issued the final airworthiness directive on the 18th of June 2025, which is just 6 days after the crash. And there is, in my view, a possible link in timing from the final FAA notice put out on the 18th of June, mandating these checks on the water system leakage possibility, mandating checks on the seals and the moisture barrier tapes and so on.
But the bottom line is airlines should have followed the Boeing issued alert on the 6th of March last year.
Indeed.
Yeah. So, I mean, if you get an alert from Boeing or Airbus, you're supposed to do it immediately or whenever they say you must do it. And that was before the next flight. So
Yeah.
pretty black and white.
And there was, before the next flight was mentioned 6 times in that alert.
Is that right? Yeah.
Yeah.
Yeah. So is a combination, sorry, start again. Is a combination of water seepage on rotation, catastrophic electrical failure, and intermittent thrust from clogged fuel lines, where engines are relying on suction feed by the engine-driven fuel pump, a possible scenario which explains what we observe?
Unfortunately, yes. There is evidence that this was a one-engine inoperative takeoff. The aircraft appears to slow and not reach the final V2 speed. The RAT was deployed and the ADS-B transponder stopped just after rotation, a few seconds into the initial climb. The combination of a loss of thrust and a catastrophic electrical failure is a possible scenario that caused the Air India 171 crash.
Now, you've said, Richard, that the ADS-B transmission stopped at 13.38.50871 local time. But that could be simply because the ADS-B receiver went out of range or reception was impaired by a building.
Yeah, that's a possibility. So I checked all other flights on the same day, different airlines, different aircraft types, and they were all taking off on the same runway and in the same direction. And they were all picked up by ADS-B with a continuous stream of data,
Mm.
both before the Air India crash. They closed the airport then for 3 hours. And then after that airport was reopened, so no other flight shows a problem with the continuous ADS-B stream of data every few seconds. So it is possible that there was a catastrophic electrical failure on Air India 171 at around 13:38:51 local time, just after rotation, and on top of a one engine inoperative failure on departure and a fuel flow issue with a partially clogged filter somewhere. I'm not saying this is what happened. I'm only saying this is a possibility, a scenario which explains what we observe. There are other possible scenarios, which leads us to the next episodes on possible scenarios. On Monday, we're planning an episode called Uncommanded Software, which goes into the incidents around software issues where flight crews have been taken by surprise. And, we went into Qantas 72 and we've talked about the shutdown of the Rolls-Royce Trent 1000 engines on landing with the Anna 985 incident. So, and there are several others out there. We'll go through those.
Yes, if that scenario, the possible scenario, ends up being what happened, it's certainly going to be a Swiss cheese or a pink swan event, isn't it?
Yeah, well, the scenario we just outlined requires three different issues happening
Mm.
in quick succession.
Now, Richard, some viewers have mentioned that there was torrential rain during the pushback and engine start, and that relates to that report that's floating around on the internet.
Yeah. The immediate problem I have with that scenario is that there was zero rainfall at Ahmedabad Airport, both during the time that the aircraft VT-AMB was on the ground at the airport on the 12th of June, and during the time it was taxiing and taking off. One of the viewers said that there was a Boeing Emergency Service Bulletin, SB-787-24-212, and it was issued on the 15th of June, and it mandates replacement of power relay box PRB-A connectors with sealed versions designed to prevent moisture intrusion into the power distribution system of the 787. Well, sorry, but this is fake news. And it's just a rumor circulating in social media and on various chat forums. I could not find this emergency service bulletin on any Boeing, FAA, or EASA website, which I am constantly monitoring.
Yes, there's about, I think I've counted now, there's about 4 versions of that supposed preliminary report. They're all basically the same construct. They've come from the same place, but they paint 4 different scenarios, all of which are completely incorrect.
Yeah, so I find it amazing there are people out there who just want to spread misinformation, and we've, as you say, we've had several of them now, and you have to be, yeah, careful what you read and what you believe.
Yes, you do. As you suggest, we're coming back on Monday with a special episode called Uncommanded Software Incidents or Scenarios. And tomorrow we're going to come back with your questions from this episode and some of our previous episodes. So, viewers, please subscribe to us, please like us, please keep those comments coming. We really appreciate them. And please keep the questions coming. They're absolutely fantastic. And Richard, thank you very much indeed for all the work you've done on this today. Really appreciate it.
You're welcome.
And viewers, please tune in tomorrow for another edition of Daily Airline News, focusing on the tragic loss of Air India 171. Thank you.